Now we'll begin 17.2, heat in the atmosphere. Vocabulary list here is for 17.2. If you have not recorded your vocabulary and the definitions in your lab notebook at this point, please pause this and do so. And also make sure that you look through the headings and read through this section before you begin. The objectives describe how energy from the sun moves through the atmosphere by radiation, conduction, and convection. Identify the characteristics of each atmospheric layer and analyze Earth's heat budget. Radiation is the transfer of energy through space in the form of electromagnetic waves. It is the first of three ways heat energy moves. Heat energy enters and moves through the atmosphere, and energy from the sun reaches Earth through radiation. The forms of radiation include radio waves, which are the longest wavelengths, followed by microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. This is what we call the electromagnetic spectrum. We use electromagnetic waves for many things. A couple of those would include radio, television, X-rays, and images in space. Conduction is the second way heat energy moves, and it is the transfer of heat through collisions of atoms or molecules of a substance. The two examples given: the bottom of the pot touches the burner and is heated by conduction. The water touching the bottom of the pot heats by conduction. And finally, we have convection. Convection is the transfer of heat energy in a liquid or gas through the motion of the liquid or gas caused by the differences in density. The heated water is less dense, and so it rises, moving heat upward by convection. As it moves away from the conducted source of heat, it cools down, the density changes, and it sinks back down. This is a cycle. So looking at this diagram, again, we'll have questions, and I'd like you to pause and answer these questions at this time before I show you the answer. What direction is heat being transferred in the water? Upward. You can see the convection cells. Everything is moving in an upward direction. What is this kind of heat transfer called? Convection. It's cyclical based on the density of the water. Now, temperature is a measure of the average kinetic energy of the atoms or molecules in that substance. Molecules of water that is almost boiling move faster or more rapidly than molecules of water that is nearly freezing. For this reason, temperatures of boiling water is greater than the temperature of freezing water. Now, heat can be thought of as the total kinetic energy of all the particles of a substance. A thermometer measures temperature, not heat. Scientists measure temperature using a Celsius scale, which is based on the properties of water. At sea level, ice melts at 0 degrees Celsius, and water boils at 100 degrees Celsius. There is a comparison of Celsius and other temperature scales, as you can see one to my right. So heat is the total kinetic energy of all the particles of a substance. Let's try to convert 70 degrees Fahrenheit to Celsius. If you are using the classroom textbook, see page 696 at this time to get an accurate conversion. You can use the scale on the right, locate 70 degrees Fahrenheit, move across, and get as close as possible for an accurate measurement. If you got 21.1, you did your calculation correctly. If you rounded it and you did it visually, you might have gotten 21 or 21 and a half, maybe even 22 degrees Celsius. When do you often see the Fahrenheit scale used? In weather forecasts, on oven dials, on household thermometers. When do you often see the Celsius scale used? In science experiments and textbooks. We will be using the Celsius degree in most of our work in class. Now, heat moves by radiation, convection, and conduction. The atmosphere is divided into layers based on its temperature. Looking at this diagram, which layer receives the most intense solar radiation? Before I answer this, let's look at each layer independently. Down on the bottom of the graph, you can see a temperature scale on the x-axis, and you you can see the height above the ground in kilometers, which we will call altitude, on the y-axis. You can see in the troposphere the temperature is warmest near the surface. Now the troposphere is the lowest layer of Earth's atmosphere. The temperature decreases with altitude. Now most of the sun's radiation is absorbed at Earth's surface, 51%, which in turn transfers heat to the atmosphere through conduction and radiation. So the air at the surface is the warmest, and it generally decreases with altitude or the distance from the surface. Now the rate of cooling with altitude varies from place to place on the planet, but on average the decrease is about 6.5 degrees Celsius for every kilometer gained in altitude. Now the temperature stops decreasing at what's called the tropopause. That's the area between the troposphere and the stratosphere. The altitude of the tropopause varies according to latitude. At the equator it's about 16 kilometers, and at the poles it's about 9 kilometers. The jet stream technically is below the tropopause, although the jet in this diagram is above it, so we consider it near the tropopause. Now the density of the atmosphere changes. Most of the density in the atmosphere, or the highest density in the atmosphere, is in the troposphere, where 80% of all the total mass of the atmosphere is in the troposphere. It also contains the most water vapor, which in turn is the reason why almost all of Earth's weather occurs in the troposphere. Then we begin our track into the stratosphere. Now the stratosphere is a very clear and dry layer of the atmosphere. The lower part of the stratosphere is about as cold as the tropopause. The upper part of the stratosphere warms up steadily and is about 50 kilometers above Earth's surface. Now the temperature increases in the stratosphere because of the presence of the ozone, which is a form of gas. We'll learn about later in this section. The ozone absorbs ultraviolet rays from the sun and then releases some of this energy in the form of heat. The stratosphere ends at the stratopause. Then the mesosphere begins. The mesosphere ranges between the 50 and 90 kilometer mark above Earth's surface. It has very little ozone, and the temperature again drops with increasing altitude. Now above 90 kilometers lies the atmosphere's fourth layer. After the mesopause, the thermosphere. This is where the atmosphere is greatest in altitude. It's extremely thin, but the few molecules and atoms present receive such intense solar radiation that the temperature can rise above 1000 degrees Celsius. Now the thermosphere is separated into different layers of gases. The heavier gases are in the lower levels and the lighter in the higher levels. Thermosphere receives the most intense solar radiation. Which layer contains a gas that absorbs ultraviolet UV radiation from the sun? Stratosphere. Which is the gas called? What is this gas called, and what is it? It's the ozone. It is a molecule made up of 3 oxygen atoms. Where is the jet stream? Near the tropopause. Where does most weather occur? In the troposphere. There are a few more videos to go more in depth on the layers of the atmospheres and their properties if you wanted to go and check these out. Now Earth's heat budget represents a flow of energy into and out of Earth's atmosphere. This diagram is based on average data. Now clear skies, cloud cover, snow-covered ground would affect these values. But we're going to start off with 100 units of insolation. So if we have 100 units of insolation, which is the radiation from the sun, entering Earth's atmosphere, 30 units would reflect or scatter back into space. 19 units would be absorbed by the atmosphere, and 51 units would be absorbed by Earth's surface. Now 6 units radiate directly from the surface back into space. Evaporation transfers 23 units into the atmosphere, 15 units are radiated from the surface to the atmosphere, and then 7 from conduction and convection. So if you add these up, 6 units radiated back to space from Earth's surface, 64 units are radiated back from the atmosphere, and the original 30 units reflected or scattered back to space, you add these three totals up, it's going to equal 100, which is what came in. Now, an imbalance in Earth's heat budget causes changes to Earth's mean temperature. Earth's system receives only about 1/2 billionth of the sun's rays. Incoming solar radiation is called insolation. Which part of energy budget shown would be affected by an increase in the gases that contribute to the greenhouse effect? Potentially all upward pointing arrows originating within Earth's atmosphere. So all 70 units pointing upwards. Now ozone, which is a molecule of oxygen that consists of 3 oxygen atoms, the ozone depletion comes from chlorofluorocarbons, or CFCs, and are stable at low altitudes, but when they reach the stratosphere they react with UV radiation and release chlorine molecules. These chlorine molecules break the bonds between the 3 oxygen atoms. If you click on the link, you can go to NASA's source for these images. You can see here, these are in Dobson units. 200 is the lowest, 400 is the highest. You can see what the changes are between 1982 all the way to 2012. Natural emissions and pollutions. Emissions of pollutants, and this can tell you what's happening with each of the 4 different types of pollutants from 1970 up until 1998. Some of these pollutants have an effect on the atmosphere. This effect is called the greenhouse effect. Much of Earth's heat energy would be lost to outer space if we did not have any greenhouse gases. Earth's average surface temperature would be about 33 degrees cooler than it is now, which is freezing. The greenhouse effect has actually helped Earth thrive as a planet. However, there's been a significant increase in the levels of carbon dioxide, which is another greenhouse gas, in the atmosphere, and the Earth's heat budget may be becoming out of balance. Many scientists warn of the possibilities of global warming. That concludes 17.2. Please check out 1 through 6, the section review questions for practice items. Thank you.